Okay, hello everyone. So back again with another data analysis video. Still focusing on data visualization, exploring data through plotting and creating visualizations. So in this video, I am just going to focus on a particular method for creating visualizations of the distribution of variables that is available in the Seaborn software library, and that's the seaborn displot, DIS plot, which is short for distribution plot. So this is kind of a very quick and easy way to create plots of the distribution of a variable or joint distribution of more than one variable. And it's a method that has a lot of functionality. It combines, it's very versatile, and it combines histograms with kernel density estimators, and you're also able to obtain something called the ECDF, which stands for empirical cumulative distribution function, and you will see what those are in a sec when I create some of them. So in terms of KDEs, kernel density estimators, and ECDFs, empirical cumulative distribution functions, I will create separate videos on how to create those. But in this particular video, I'm going to show you kind of the displot method and some of the different elements that you're able to use, some of the different parameters you're able to create, and hopefully it will convey how useful that is, how good a method for plotting the distribution of variables this is. So no matplotlib as such to create plots in this particular video, just the Seaborn, one particular method from Seaborn, which I think is very versatile and quite easy to use and useful. Okay, so to start with, I'm going to import some libraries. I don't think we need all of these. We really only need matplotlib, which is the base that Seaborn is built from, and Seaborn. But I'll import pandas and numpy as well, just in case I decide to use them to demonstrate anything. So I've imported pandas as PD, numpy as NP, matplotlib.pyplot as PLT, and Seaborn as SNS. So those usual nicknames for those particular libraries. And in previous videos where I have kind of imported a data set, one of my own data sets, or a data set that I've got saved, that's available online, that I've got saved as a CSV or a spreadsheet on my actual computer, I'm going to do something slightly different in this particular video. I'm going to import a data set that is available within the Seaborn software library. So often software libraries for plotting or to do other things within certain programming languages will have embedded within them, they will have data sets available to allow you to play around with and practice using those particular libraries. And Seaborn's got a few contained within it, and I'm gonna basically use one of those data sets. I'm going to just load up one of those data sets that's kind of embedded within Seaborn, and it's called penguins. And in order to do that, I'm going to create an object called penguins, the data frame object, and I'm going to use the command I'm going to give it is sns.load_dataset, and then I'm going to pass the name of the data set, which is penguins, as a string within quotes. I've used double quotes here, you could use single. So the example I'm going to use here is the one, if you go onto the Seaborn website and look at the guidance on how to use Seaborn, it's the example that they use for using the displot method. So I got a lot of this from there, and you'll be able to see the coding examples are quite similar. But what this data set is, penguins, is it's data relating to 3 different species of penguin, I believe, and various measurements in relation to them, such as the length of their bill, the length of their flipper. There's a few others there as well. We'll see. I think we'll see as we go along. Cumin, which is like the how large the bill is from kind of the dorsal side to the underside, something like that. Okay, so lots of things we can do with this. So first of all, I'm just going to create a displot the standard. All I've done is I've used sns.displot, DIS. There used to be a method in Seaborn which is now deprecated, which was called displot, DIST plot, and it did much the same stuff as you get with displot, but it's now changed. There's no T, it's just DIS plot, but it's short for distribution plot. And if I run this first cell, what we're going to do is plot the distribution of flipper length for all the observations in the penguins data set. And you can see there flipper length on the x-axis range from between like 170 and to about 230, and it's got a count frequency of observations for different kind of measurements, 190 to 195 there. There seems to be about 80 observations, 80 penguins with that length of flipper. Okay, so the default then, as you can see from this, is a histogram. It's plotted as bars, like they're discrete bins as such. But what we can do is change the argument. We can plot the same thing again. So we want flipper length is going to be our variable on the x-axis, but we're specifying the kind of plot we would like using this kind argument here. And I'm asked for KDE, so a kernel density estimator. Okay, so that will effectively just give us a continuous probability density function of what the data is, how the data is distributed. So if I run this cell, what we should see is kind of similar shape to this, but like as a continuous kind of line there. So we can see we've got this interesting bimodal trend going on for both. And all I've done there is just change that default and specify the kind we want is KD, a kernel density estimator. Yeah. And so the next one I mentioned it in the introduction, is empirical cumulative density functions. So ECDFs, I will make a separate video on them because I'm kind of quite interested in them. I think they're really good and can be very informative. They can be more informative, I think, than this type of histogram plot for looking at distributions, and the same for this. But this is what so anyone familiar with a cumulative density function will know that it's monotonically increasing like this, and the proportion here will add up to 1. So all observations in the data set will add up to 1. So we've got flipper length on the x-axis again, and you can see, so let's say by the time we get to 200 mils, if we were to follow that up, we're almost up to we're probably up to nearly 55% or 0.55 of the data of the observations have a flipper length of 200 mil or more, and 100% of them have 230 mil or less, if you see what I mean. Sorry, that should have been 200 or less. Okay, so what's useful about this, I find, is if it's got this kind of S-shaped distribution to it, it's sort of, that would be like a sigmoid shape, and that would represent your kind of normal distribution. We know that this variable isn't normally distributed. It's got these two peaks, so we can see that the line is a bit more wonky in the middle. There's this peak here, and there's probably a smaller one here at higher values, close to 220, and it doesn't flatten off really until right up to the maximum sort of length of 240. But what's useful is whereas it's hard to tell how many individuals kind of they were for different, how many different measurements, how many individuals there were for different measurements with a continuous distribution like this, because it really has density of 0. We can only talk about proportions between certain values and how they sum. If we kind of look at this, the height of each bar gives us some indication that multiple individuals. So if we were to look here at like a height of about 190, a flipper length of about 190, you see we've got this long straight bar here. So we know from looking at that about, that's possibly about 5%, 5% of the data observations, maybe that counts for, had a flipper length of about 190. So ECDF is quite useful, especially when you plot more than one on the same plot and you can see differences between groups. We'll see that shortly. Okay, so we can combine those, the first two though, like a histogram and a kernel density estimator. And the way to do that is rather to just get the KDE, we just set the kind equals KDE. But if we use this argument where we say KDE equals true, it will plot the histogram and it will overlay the kernel density estimator over the top of it, which is pretty good. It looks pretty good, I think. I personally find that I think these ECDF plots and KDEs are more useful than histogram in many cases for understanding distribution of data. Okay, so that's plotting just one variable at a time. So we only looked at flipper length there, so distribution of one variable. We can look at the joint distribution of variables by specifying one variable on the x-axis and one variable on the y-axis. So if I run this cell, what you can see here is we've got flipper length on the x-axis and bill length millimeters on the y-axis, and it's kind of doesn't look great as a plot. We'll see a slightly different type in a minute that looks better, essentially. But this is almost like you were looking down on a histogram of two variables, the distribution of two variables from above, and these darker colors represent kind of like higher densities, so to speak. So this dark point here and this one here would represent those two kind of peaks on the flipper length variable, but they're also the distribution of scores is obviously, we've not looked at bill length on its own, so we can't really say too much about that. I'm not massively keen on that. I think it's kind of useful to do that, and it could be quite useful if it's not hugely granular. Gives us an indication we've got a lot of individuals clustered around here and around here. But we can get a similar plot but ask for a KDE plot. And this is the same two variables, but the KDE version. And these circles, these concentric circles, are almost like different. They're like gradients, I suppose, on an OS map. So the closer they are together, the higher they are. So what you can see here is we've got this. This is kind of a hilltop if we're looking down on it from above, and this is a hilltop, and those would represent the. If we were just looking from the flipper length axis at this side on, they would represent that bimodal shape. But I think that is kind of more informative there. You can see there was this kind of slightly darker area here as well, and that's kind of represented by this kind of gradient circle, so to speak. But that is kind of a bird's eye view, like a view from above of a KDE for the joint distribution of those two variables. I think that's more informative than this one. It looks better as well. Okay, there's something else you can do, and that is kind of you can add what are known as rug elements to the plots. If I run this, I'm running this, and the only thing I'm changing from the above one is I'm setting this rug equal to true, and you will see what that relates to here. So what it does is it creates these kind of fringes on the edges, almost like the frill around the edge of a rug plot, essentially. I guess that's where that comes from. And the darkness of the bars kind of represents the density. So it's a similar sort of, if we were to look at from above at these two variables individually, we'd kind of see here the density is much higher here. so it's darker and things are closer together, and the same here. This one is kind of a bit hard to see with the flipper length one, but these are closer together here because we know we've got this peak and these. I'm kind of undecided as to whether I like rug plots. You sometimes see them on different, you can put them on lots of different types of plots. They can be informative, I think, in some ways. They don't look too intrusive here, and as long as someone understands what they are and how to interpret them, they're not problematic. But in many occasions, I can't really think of why I bother using one, to be honest with you. All right, let's look at similar sort of thing. We're going to ask for a KDE plot. We're just going back to we're just going back to plotting one variable, so just flip a length. We're not looking at joint distribution now, but we're going to use the hue argument to specify different groups. So species, there are 3 species in this data set. If I run this, what you will see is we've got this nice KDE distribution plot, and it's separated out by the 3 species of penguin in the data set. So blue is Adelie, orange is chinstrap, and green is the Gen 2 penguin. So in terms of flipper length, you can see species difference in flipper length for these 3 particular species. That's quite an informative plot, and you know, this really useful that using color we can separate out groups and plot them on the same plot, see where the differences lie. Another way to do it, we can also add multiple equals stack. You've seen something similar when we looked at histograms before, where it creates a histogram, but it breaks down each bar by the relative contribution of each species, so they're stacked on top of each other. And when we looked at histograms, there were a few different, we could use you could use the step thing where it kind of just showed you the outline of the bars for each species. Sometimes if you've got a lot of different data you're plotting, it just looks messy and the colours clashes. But this stacked version here I think is quite useful if we're looking at flipper length. It gives us some sort of indication of differences between the 3 species that's probably not as easy to interpret as the KDE there, but kind of you can see what the information that it's conveying. A lot of Adelie penguins here have smaller flipper length. The chin straps kind of slightly larger, but not much different to Adelie's. And the largest flipper length for these penguins, it seems to be occupied. It seems to be the Gen 2 penguins, the larger species. Okay, so something else we could add is this col argument, and so we're getting quite granular here. This relates to columns, so what this is going to do when I run it is going to create those kind of small multiples, those kind of facet grid plots that can be quite useful. So you can see there we've created our KDE plots separated out by species, and then we've separated again by sex. So this first plot, so this would be column 1 here, which relates to males, and this would be column 2, which relates to females. So pretty useful there. So we can look at the differences between species, and we can separate them out by another category, say sex in this case. Quite nice plots. I am a fan of KDE's kernel density estimate plots when we're inspecting distributions. They're not influenced by bin size, and they seem to give us a good honest impression of how our data is distributed. Okay, so one last thing to look at though is we looked at an ECDF up here for a single variable. We can do a similar sort of thing and separate out by, say, sex, using different coloured bars for sex, and even separate by small multiples, so multiple plots, using our columns argument. And I've set a couple of parameters in terms of height and aspect as well. If I run this, what you will see, that's just kind of so they'd squeeze on. So I've separated by species in terms of columns. So it's given us three columns, three plots, all on one row. The first one relates to Delhi, the second to Iraq, the third is Gentoo, and the thing we're looking at is flipper length, and proportion is on the x-axis this time. So remember, that's going to sum to 1. The proportion is always going to sum to 1, 100%. Think of it like a percentage. And the different coloured lines represent sex. So this, as I was saying before, I really like. So the length of the bars this time would be going horizontally in terms of how many data points they were accounting for. But I really like these ECDF plots because I think they can be easier to interpret where you have differences in some ways than a CDF essentially. So what you can see here is flipper length separated by sex. Males are in blue, females are in this yellowy orange color, and you can see the difference between the two. Across the species, so these plots are kind of demonstrating quite an interesting aspect of biology, that you get sexual dimorphism in body size within penguins between males and females. Okay, so, and if we look here, say for example, in terms of flipper length, if we look at about 210 there, quite a number. A large proportion, from maybe almost like 20% of the female Gentoo penguins have a flipper length of about 210, that type of thing. It's quite informative plots. Yeah, I really like them. Okay, that's it. So that was how to use the displot method in Seaborn. Really easy to use, kind of simple 1 lines of code. There are a number of other elements you can add to customize your plots and things like that. Check out the website, the Seaborn website, and the guidance for that. Yeah, that's it. Pretty good. A really versatile and good way to plot the distribution of a variable.